Welcome back to our last lecture of Physics 1111. This is lecture number 24, Waves and Sound. So we have already looked at simple harmonic motion. We can think about having a mass on a spring, we pull the mass down, we release it, and the mass oscillates up and down and up and down. But now let's imagine that rather than a single mass, we have a whole series of masses. So we've got a whole bunch of identical masses, all on identical springs, all in a series like this. Okay, and that just keeps going. And then each mass is connected to its neighbor by another spring. Okay, etc., etc. Now let's imagine what happens if I start moving this mass up and down. Well, because of this spring here, it's going to apply a force on this one. So as I move this one up and down, this one will start moving up and down, which will make this one start moving up and down, which makes this one move up and down, etc., etc., etc. So when I move this mass up and down, there's going to be an oscillation that propagates, a movement that propagates through these masses. That's what we call a wave. There will be a wave that propagates through the masses down in that direction. Excellent. Now, there are a couple of different kinds of waves I would like to talk about, and that depends on the kind of motion that we have for this mass. Do we move it up and down like this, or do we move it side to side like that? They create a different kind of wave, and I want to distinguish between those two. If I move the mass up and down, I'll get a wave that looks like this that propagates off in that direction. The motion of an individual mass is in this direction, perpendicular to the velocity. When the oscillation is perpendicular to the velocity, we call that a transverse wave. Now, if I moved the mass back and forth this way, I would end up with an oscillation of all these masses in this direction, which would be parallel to the velocity. That type of wave is called a longitudinal wave. So here we actually get a physical displacement of the wave perpendicular to the velocity. Here we can think of this as variations in the density, perhaps, of the masses relative to the average density. The masses in this case are moving back and forth like this. Now, either of these types of oscillations we can graph on a graph of time. We can either graph, say, physically, the physical displacement of the motion, something like that, or in this case, we could graph the density of the masses relative to the average density. So we'd have, say, a larger density here, a smaller density here, a larger density here, like that. So again, we can graph either of these and get something that looks kind of like a sine wave. So let's imagine we graph that. Let's look at some of those properties. So here we have a wave plotted as a function of position on our oscillating medium, whatever it is, the masses on the springs or whatever the material is that the wave is going through. Here we have either the displacement or the density or whatever it is, whatever oscillation that we're plotting. Different kinds of waves can have different kinds of displacements or whatever. This could be a sound wave where we're measuring density. It could be a wave on the masses where it's actually a physical distance. Could be an electric field where this would be an electric field variation. All sorts of different kinds of waves. The distance from one peak to the next peak, that's what we'll call the wavelength. The units of wavelength are always in meters. It's a physical distance. The symbol that we'll use for wavelength is a lowercase Greek letter lambda. The amplitude is the distance from the equilibrium value to the peak of one of these oscillations. That's what we'll call the amplitude. Now the units of the amplitude will depend on whatever kind of wave it is. It could be meters, it could be a density, or it could be electric field units or whatever, depending on what kind of wave we're talking about. Now imagine that we stand over here we stand over here and we watch these waves go by. We measure the time for one wave to pass by. That's what we call capital T, the period. The period is the time for one wave to pass by. And the units of the period are seconds. We could also measure the number of waves that pass us per second, and that's the frequency, which is then 1 over T. T is the number of seconds per wave. The number of waves per second would be 1 over T. That's what we call the frequency, and the units of frequency are hertz. Okay, great. Let's imagine that we're watching a particular wave go by. We're standing over here, and let's imagine that this wave has a frequency of 3 hertz. That means that 3 waves pass us by every second. Let's imagine that the wavelength of the wave is 2 meters. So each wave is 2 meters long. So how far does this wave move in 1 second? Well, if 3 waves pass us by in a second, each wave is 2 meters long, what length of wave pass us? Well, in 1 second, 3 waves, each wave 2 meters long, that's 6 meters. So 6 meters of wave will pass us in 1 second. So how fast is the wave traveling? 6 meters per second. Now how did we get that? 3 times 2. Well, this is a very, very general result. The speed of a wave is equal to the frequency of the wave times the wavelength. And that is a very, very general result. Let's stick some numbers in here and see if we can figure out a wavelength for a particular wave. One of my favorite radio stations here in Atlanta is the River 97.1. Let's see if we can figure out what's the wavelength of this radio station. Now 97.1, what does that mean? Well, that's the frequency of the radio station. What are the units? 97.1 megahertz. In other words, the frequency of that radio station is 97.1 times 10 to the 6th hertz. Now, it's a radio station, which means it's giving off radio waves. Radio waves are a type of electromagnetic radiation, and all electromagnetic radiation in a vacuum, and pretty close to it in air, travels with a speed of c, which is 3 times 10 to the 8th meters per second. So let's figure out what's the wavelength. We know that lambda f equals c, so lambda is c over f. In other words, 3 times 10 to the 8th meters per second, divided by the frequency, 97.1 times 10 to the 6th hertz. Hertz are cycles per second, or inverse seconds. Divide that out, and what do we get? 3.09 meters. Well, that's about that's 1, 2, 3, just a bit out of the screen, I'm afraid. Just about the size of our screen view here is just about 3 meters, a little bit more, 3.09 meters. So that is about the length of the wavelength of the wave that's used by the river 97.1 that carries its signal. Okay, great. Another very important type of wave, other than electromagnetic waves, are sound waves. Sound waves are pressure waves that travel through air, or they can travel through other materials. You can have sound waves in water or other liquids. They can travel through the earth. Earthquakes are kind of like sound waves traveling through the earth. Very, very low frequency sound waves. But for us, when we're hearing something typically in air, we're talking about a pressure wave in air. Now, to make a pressure wave, you basically just need something that's moving through the air. Just like we were talking about moving the masses back and forth, that when we moved the mass back and forth, it created that density wave that traveled through the hanging masses. Well, if you move something back and forth in air, when you move it forward, you compress the air in front of it. And when you pull it back, you rarefy the air in front of it. And those then propagate off away from the object. Now, I'm making sound waves right now. but you can't hear it because the frequency that I'm making them, 1, 2, 3, 4, is about 1 hertz, 1 cycle per second. Now, our ears can hear from around 20 hertz to around 20,000 hertz. Now, that's actually someone with very, very good hearing. Typically, as people get older, they start losing their upper range of hearing. I know that I can hear only to about 12,000 hertz. As people get older, they start losing that upper range of frequency. But let me just demonstrate that a little bit. I have an oscillator here that I will hook up to a signal generator, and this will just move up and down and up and down, and actually will make sound waves. And I can make low frequency and high frequency sound waves, and we'll listen and hear what they sound like. So here you can see this is going 1, 2, 3, 4. I have it set to oscillate at about 1 hertz. So you can't hear it as a sound. You can see it oscillating, but it's not making a sound that we can hear because, again, the frequency is too low. But I can turn up the frequency. Now, that frequency is at 100 hertz, and hopefully you'll be able to pick that up over the microphone. You can probably hear it better like this. That's 100 hertz. That's 200 hertz. So as I increase the frequency, you can hear the sound increases in pitch. Now, we can hear that change in frequency as a change in pitch up until several thousand frequency and several thousand hertz, and then we kind of lose the ability to distinguish different frequencies. We can still hear it, but we can't hear the change in the frequency as a change in pitch. Okay. Now, the amplitude corresponds to the loudness. How loud is the sound? So I can turn down the amplitude and it sounds softer. It's not as loud. If I turn up the amplitude, it gets louder. So the frequency, as long as it's not too high, we distinguish as pitch for the most part. And then the amplitude we hear is how loud the sound is. There are actually some other psychological and physiological effects that also affect how you perceive pitch. But basically, for us, it's just what the frequency is. That's good enough for us for now. Under ideal conditions in a laboratory, some people have been able to hear frequencies ranging from 12 hertz up to 28,000 hertz. So that would be someone with exceptional hearing in ideal settings. However, we can only hear from, say, around 16 to 16,000 can we distinguish pitch. And we can actually hear about 1,500 different pitches. If the frequencies get too close together, we can't distinguish them as different pitches. Now, there are sound waves outside of this range that just we cannot hear. Sound with a frequency higher than 20,000 hertz is called ultrasound, while sound waves with frequencies lower than 20 hertz are called infrasound. And there are some animals that can actually hear these. For example, elephants can hear frequencies around 14 to 16 hertz, much lower than us, typically. Some whales can actually hear frequencies of 7 hertz underwater. Some bats can actually hear frequencies above 100 kilohertz, above 100,000 hertz. For example, ultrasound is also used if you've ever heard about someone that was pregnant having an ultrasound. That's basically just using sound waves at a very high frequency above what is typically heard. Now, there's something else that I think is kind of an interesting sound light phenomenon that I'd like to talk talk about just for a minute. Have you ever heard the adage about if you hear or if you see a lightning strike and then hear the thunder afterwards, you can figure out how far away the lightning strike was? I'd like to talk about that for just a second.